Hello, this is Mr. White, and this video is on antiderivatives, or indefinite integrals, part 1. So as you look at the 4 exercises for today, I want you to recognize that there's really the same objective in all 4 cases. They may be presented or asked in a different way, but this is all about anti-deriving. I'm going to further that case here in just a moment. Let me get rid of that. I'm going to just move this one down lower here. Okay, so to further that argument here, you could just anti-derive right off the bat. Nothing wrong with that. But I want to show you where the indefinite integral symbol can fit in. And that's the symbol that sometimes students refer to as the squiggly thing when they're brand new to it. If we start by multiplying both sides by dx, cancels on the left, and I end up with a dy. And just for emphasis, I'll put 1 dy. Equals 7x cubed dx. And then, if I put an indefinite integral symbol here, and whatever I do on the left side, I got to do on the right. And we remember that what that's asking us to do is find the function whose derivative is 1. What function do you derive and get 1? Well, most students would say x, but remember that's part of the purpose of this differential here, is it tells us we're not dealing with x on the left side, we're dealing with y. So we say when you derive y, the derivative of y is what's going to give us a 1 with respect to y here. Okay, so that's what equals the antiderivative of 7x cubed dx. And so again, I'm not saying that you had to do these 2 steps that I just showed here, but I wanted to show you that this is basically the same question. If you're asked to find the antiderivative presented this way, or if you're asked to solve the differential equation as it was originally asked, same thing. All right, and when we ask ourselves, what function do we derive? We turn our attention to the right side, and we say, what function do I derive to get 7x cubed? Well, we know that when we power rule something, that the exponent reduces by 1, so we know that beforehand the exponent must have been a 4. And again, we're kind of ignoring the 7 for just a moment, so let's cover that up for just a moment. And if the exponent was a 4, and I imagine now deriving x to the 4th, I know that that 4 would be multiplied in front, right? So I'm going to need a 1/4 to balance that out. Take a moment, derive that in your head, and convince yourself that when you derive 1/4 x to the 4th, you get x cubed. Okay, convinced? So we know that if I now uncover this 7 here, that was hanging out all in front, all along. That was the constant multiple rule, as we call it. And since I have just anti-derived, this is the part, or this is the time at which you remove these 2 symbols. We won't write them anymore because we've just anti-derived. And there's one last thing we have to do besides simplifying. We have to recognize that really you can add any constant after here. If I'd put plus 5, for example, well, if I derive this function, deriving the 5 is just going to give us a 0, right? And so if I derive this function here, I'll still get 7x cubed. So really, there's nothing special about 5, of course. We could put any constant there. So that's the purpose of the plus c, is to recognize that you could derive any constant c, and it won't make a difference in your final derivative right here. Okay, so let's just simplify that a little bit. And we'll put y equals 7/4 x to the 4th plus c. And it really is a habit you want to get into, where when you're done anti-deriving, just mentally or on paper, derive that in your head. Okay, 7/4 x to the 4th. The 4 comes down, gets multiplied by 7/4, that gives me 7. This x to the 4th becomes x cubed, so 7x cubed. The derivative of c is 0. So my derivative of 7x is 7x cubed. And look back up and make sure that it matches the original. I can't emphasize that enough. That's just a habit you need to get into. Derive your final answer. And that's actually what was asked of us at the beginning when it said, check the result by differentiation. Start making that a habit. Okay, so we're done with that first one. And let's turn our attention to the second one now. Okay, let's notice that it's really the same thing. And I included this in the video because every year students get thrown off whenever we include something other than just x's and y's. If I go back to that original problem, to compare these two, and notice that they're really the same thing. The derivative of y with respect to x on the left-hand side gave us a constant times the variable x to the third power. Well, same thing on the right-hand side. The derivative of some function w with respect to variable h gives us a constant times the variable h cubed. And remind yourself, e is a constant. It's not a variable, so big difference. E, pi, any other kind of special designated symbol like that, treat it as the constant that it is. So this time I won't go through the whole process of writing the antiderivative symbol, or the indefinite integral symbol, but I will cover up the constant temporarily. Due to the constant multiple rule, we can do that and just say, let's antiderive h cubed. And as we discussed before in the previous exercise, you'll get h to the fourth. The exponent goes up 1, and then we need that 1/4 in there to balance it out when we apply the power rule. So I'm mentally already checking it in my head and saying, if I derive this, do I get this? Answer is yes. Okay, we reveal the constant that was hanging out all along, e to the fifth. And since I just anti-derived on the right-hand side, I anti-derive on the left-hand side, and I get just w. And then we remember the plus c. And then we get e to the fifth over 4, h to the fourth, plus c. That's our final answer. Again, very similar to the first one. All right, let's go on to the next exercise. So upon seeing an exercise like this, students frequently at this point in the year would comment, oh, that looks like we're going to use the quotient rule. Now remind you, no, the quotient rule is for deriving, not anti-deriving. And if you're wondering, is there any anti-deriving equivalent to the quotient rule? Well, no, not really. So what we will do, similar to how we've always done, is we will tackle that algebraically first and then integrate. That's still going to be a general rule of thumb, is something you want to consider doing, is do a little simplification first, and then you might make your job a lot easier. So since I'm not doing the actual anti-deriving yet, I'll still keep the indefinite integral symbol, and I'll just simplify what's inside there, contained within it. The numerator, if I FOIL it out, that's our difference of squares. That's x squared minus 3 squared minus 9 over x squared. And if I can further simplify that into a way that's going to be easy for us to deal with, we recognize that x squared over x squared will give us just 1 minus 9 over x squared. That's going to give us 9x to the negative 2. I could have written 9 over x squared, but remember, we're going to be anti-deriving next, and this form is going to make our job a little easier. Okay, now we turn our attention to going to anti-deriving, or integrating. If we integrate the 1 right there with respect to x, meaning x is going to be our variable, that means that we're going to get an x here, because the derivative of x gives us 1. Okay, as I've done in the previous exercise, I'm going to cover up that minus 9 for just a moment and focus on the x to the negative 2 power. So if I anti-derive x to the negative 2 power, be very careful of that negative exponent. Students often handle that a little clumsily. Remember, we want to add 1 to the exponent. So adding 1 to negative 2 is going to give us negative 1. And then I ask myself, what must have been sitting out in front here to balance out that negative 1? Well, if I mentally derive this, I'm going to multiply this negative 1 up top, and I need a negative 1 down here to balance it out. So again, just quickly in your head, derive this expression here, and verify that you will get this. Make sure you agree that you will get x to the negative 2. And once you agree with that, let's now unveil the minus 9 there that was hiding all along. And we'll have minus 9 times all of that. And don't forget the pesky plus c. And when we simplify that, we're going to get x, and then there's a minus minus. So it's going to be plus 9x to the negative 1. That's the same as 9 over x plus c. Put a box around it. I'm going to admit that if we were to, I've been encouraging you to get in that habit of deriving your final answer and verifying that you get the original expression. I'm going to admit that it's kind of hard to do in this case because that original expression was kind of dressed up and we had to do some simplifying first. But notice that we were along the way just mentally deriving. Every time we anti-derived, we mentally derived it and made sure that we were doing it correctly along the way. So at least that's somewhat of a check. Let's go on to the next one. Okay, this time we weren't told to present our answer in the form of a table, but it should still just be understood to us that it is in our interest to rewrite this. And how are we going to rewrite it in a way that makes our job easy? Well, we know that radicals generally don't work well for us in calculus, so we'll rewrite that as x to the 5th power, but then that cube root is the same as putting 5 over 3 there. Okay, and as far as the second expression, that's minus 3 over x to the 1/4 power. So that's the same as 3 times x to the negative 1/4 power dx. All right, let's anti-derive that first term there. And when I add 1 to the exponent, I add it in the form of 3/3. So 5/3 plus 3/3 would give us 8/3. And then when I pause and mentally reverse directions in my head and I say, what happens when I derive this? Well, I'm going to need something in front here to balance out that 8/3. So I'm going to need a 3/8 here. And then again, I ask you to mentally derive this out and verify. Do we get x to the 5/3? That needs to become a habit. All right, let's go on to the next one. And again, let's cover up the constant. Let's focus on that x to the negative 1/4. If I add 1 to the exponent in the form of 4/4, well, negative 1/4 plus 4/4 will give me 3/4. And same deal. Let's mentally derive that one. And what do I need sitting in front here to balance out the 3/4? I'm going to need a 4/3. We unveil, and we've got a minus 3 there. And let's not forget the plus c. And I hope you make sure that you fully understand why that plus c is necessary. It seems like a nuisance right now, but we'll eventually come to appreciate why it has to be there. Okay, as long as we mentally checked and made sure that this is all making sense, we go through and simplify. 3/8 x to the 8/3 minus 4 x to the 3/4 plus c. And put a box around it. And the last thing we'll do is just check. Again, sometimes you can do this mentally or you can do it on paper, whatever is most comfortable for you, but make sure you don't be lazy about it. Do it. Let's check by deriving, by differentiating. So when I check 8/3 times 3/8, and it's often difficult. If you're having difficulty switching directions, going from deriving to anti-deriving, you're not alone. It happens every year, and it just takes practice. But now we'll change directions back to deriving. 8/3 times 3/8, applying the power rule, gives me just 1. X, 8/3 minus 1, 8/3 minus 3/3 gives me 5/3. And then over here, 3/4 times 4 will give me 3. And then x to 3/4, if I subtract 1 from that 3/4, I get negative 1/4. If I derive the c, I get 0. From this point, I'm just going to, in my head, do this and say, okay, x to the 5/3, that's the same thing as the cube root of x to the 5th, so check. Minus 3x to the negative 1/4, that's the same thing as minus 3 over 4th root of x, check. And that's it. We're done.